Okay, we are doing perturbation theory, and the next point on the program is a calculation of the redshift formula as it is modified by the perturbations. This is the famous Sachs-Wolf formula and one of the most important applications of perturbation theory. So that's our next goal. And well, we know the redshift formula in an unperturbed Robertson-Walker spacetime. This was fairly simple. But now we have the perturbations, and then we need a more general formula. So what I will do first is I will derive a completely general redshift formula, which holds in any general relativistic spacetime. And then we will specify to a perturbed Robertson-Walker spacetime. So the situation we want to, so that's the redshift formula in arbitrary spacetime. So the situation is like that. In an arbitrary spacetime, we have two world lines. And we may interpret this as two observers. One is emitting light signals, the other one is receiving light signals. So the light signals move from the first world line to the second. And then when on this world line we have an interval, proper time interval, delta tau e, and here we have a proper time interval delta tau O, E stands for emitter, O stands for observer, then the redshift is delta tau E, delta tau O. Is this correct? Let me see if this is bigger than that here. The interval becomes smaller, the frequency becomes the other way around, right? It's the other way around. Then it is positive. Then the interval becomes bigger for positive set. That's what we call a redshift, yes. Okay, and to make it definite, this will depend on the interval, this quantity, and to get a definite result, one considers the limit that this goes to 0. So this is then just a derivative, right? d tau O by d tau E. So we may view tau O as we may view this as a map from tau E to tau O, and the redshift is just the differential of this, the differential quotient of this map. And my claim is that for this expression we have a very nice formula. Namely, my claim is if this is the tangent vector to the geodesic x mu dot SE, and that's the tangent vector x mu dot SO. And here we have the form velocity u e, and here's the form velocity uo. Then we have just the quotient here, that's my claim. G mu nu x mu dot of SE ue divided by g rho sigma x rho dot SO uo. So you take the scalar product of the two vectors. This is a light-like vector, this is a time-like vector. And you do the same thing here. And the quotient of these, this can never be 0, right? A time-like vector can never be perpendicular to a light-like one. So this is not 0, this is not 0. Here's a well-defined quotient, and that's my claim that this is a redshift. How do we prove this? There are hundreds of proofs. And I think the nicest and the most geometric proof, that's the one which I present now. This goes back to Dieter Brill. And actually it can be found in several textbooks, for instance in Straumann's book. So Straumann has just copied this proof from the original paper by Brill. What one does is the following. One considers this surface, the surface which is spanned by these light-like geodesics. And one labels these with a proper time of the emitter. So one has here so one labels this surface with coordinates s and tau. So s is a coordinate which starts at the emitter and terminates at the observer. So s is running along the light-like geodesics, and tau is labeling the light waves. Of course, I cannot do it in such a way that this labeling, this parameter tau, coincides with the proper time on both word lines, because this interval is different from this interval. So I have to decide which one I choose, and I choose the emitter. Yeah? So I have, on this word line, the parameter tau is just the proper time of the emitter. On this word line, it is a not proper time of the observer. It is related by exactly this quotient. Yeah? Okay, and that's how we find out what the redshift is. So I have now a surface on the. By the way, the surface may have self-intersection. This doesn't matter. Yeah. So we can. So we have just a map from a rectangle where the parameters are s and tau. A map from the rectangle into the manifold. This gives this kind of surface which may have self-intersections. And now I calculate with the help of these basic basis vectors on the rectangle. And what I want to calculate is, I want to calculate how this scalar product, ds, d tau, this is a vector field along the surface, this is a vector field along the surface, so this is a scalar quantity. And I can take the derivative with respect to s. So I differentiate with respect to s this quantity. And now I use the rules. So this is covariantly constant, so I can pull this inside the bracket with the product rule, plus g ds nabla ds d tau. And now my curves which connect the two word lines are geodesics, so this is 0, because I have geodesics. And here I can use the fact that the Levi-Civita connection is torsion-free. So this is the same as del partial tau partial s. So I can interchange the two things. Yeah? Partial derivatives commute, so there's no Lie bracket. And the fact that this is the same as this plus the Lie bracket, this is just a condition that the torsion is 0, which is true for the Levi-Civita connection. So I have now, I can now pull this derivative out, then I get 1/2 d by d tau g ds, right? If I calculate this expression, I get this here twice, and with the 1/2 in front of it, I get exactly what I want to get, right? So I pull it into the first slot, and then I pull it into the second slot, gives the same term because the scalar product is symmetric, so I get exactly this here. But my geodesics are light-like. I have light rays, so this is 0. The whole thing is 0. So what does this tell us? It tells us that this quantity is constant along each light ray, because the derivative in this direction, in the direction of s, is 0. So this means that this quantity at the left end of the diagram is the same as this quantity on the right end of the diagram. So this is g ds d tau. Let me just write it this way. O stands for observer, at the position of the observer. ds d tau at the position of the emitter. And now I recall how the tau was introduced. So first of all, this is, if I use now coordinates again, this is g mu nu. This is a tangent vector to the light ray. So this is x mu dot of s, and I'm at the observer. Yeah, it is this tangent vector. No, this one, sorry. This one. And then d by d tau, I'm at the, on the side. Let me begin with the right-hand side, because there it's simpler. G rho sigma x rho dot se. Here I have d by d tau, which coincides with proper time. Yeah? On the emitter word line, it coincides with proper time, so it is just the fall velocity of my observer. On the right-hand side, it does not coincide with proper time. If I write here the observer, then I have to correct for the fact that tau and tau tilde are not the same thing. So I have to add the, or not tau o and tau e, not tau and tau tilde, tau o and tau e. So this is d by d tau o. So I need an e upstairs and an o downstairs, right? Okay, and I want to solve for this expression. So I get d tau o by d tau e. So I take this to the other side, and then I have here g mu nu x mu dot S O. Oh, it's the other way around, as usual. Have I done it? I have O here. No, that's not true. So d by d tau is d by d tau E. No, this was wrong here. On the emitter work line, tau coincides with proper time. It's the other way around. Yeah, I have the tau E. I have the tau E in the denominator, so it's the other way around. Then it is here also the other way around. E, O, O, and that's it. That's what I wanted to prove, right? This is the redshift. So this is a proof. There are many alternative proofs. For instance, you can use a Hamilton formalism. That's an alternative way of proving this formalism. This formula, where you just make use of the fact that the frequency of light is given by the time component of the form momentum. Yeah, in the Hamilton formalism. You get the same result, of course. Otherwise, something would be wrong. Okay, and there are other proofs. In Schrödinger's book, for instance, Expanding Universes, there's another alternative proof. He uses a variational principle, a variational technique. Okay, so we have this formula now, and we want to apply this. Apply this to Robertson-Walker spacetime. With scalar perturbation, and we consider only this simple case we considered already last time, where we have just one Bardeen potential, just one scalar perturbation phi. So the metric is then G mu nu dx nu is a squared, the scale factor, then minus 1 plus 2 phi c squared t squared. T is conformal time. A depends on conformal time. Plus 1 minus 2 phi delta ij dxi dxj. That's our metric. Remember, we had a general scalar perturbation has two different Bardeen potentials. Here's a phi, and here, instead of the phi, a psi, another Bardeen potential. But we have seen that if we want to have the energy momentum tensor as that of a perfect fluid, then the two Bardeen potentials must coincide. Then we have only one. So, and that's a case to which we stick now. Of course, this is a special case because we have only scalar perturbations. You could have these vector perturbations and the tensor perturbations in addition. If you want to do gravitational waves, you would have to consider the tensor perturbations. But let's stick to the simplest case. It's difficult enough. So that's what we want to consider now. So on this space-time, we want to evaluate this formula. So we have to specify what is our observer field, and then we have to solve the light-light geodesic equation in this metric, and that's what we will do now. So our observer field, the only thing I will use is that it is a perturbed standard observer field. I will not require that it satisfies an equation of motion for dust or for a perfect fluid or something like that. I just assume that it is a perturbed standard observer field. So the standard observer field on the background would be proportional to the Kronecker delta rho t, right? Would be perpendicular on the t lines in the unperturbed space-time. And of course, because it should be normalized, I have a factor here. And now I introduce a perturbation, delta u rho. So that's the form of our vector field. And we have to determine the normalization factor n, and maybe also a condition on the delta u rho, because our u rho should be normalized. Yeah? So we require, of course, as usual, so we require, as usual, that this is normalized minus c squared. Actually, we have used this here, right? Otherwise, it wouldn't be proper time, which is associated with this observer field. So this formula only works if these things are normalized, yeah? Because we have used this in the derivation. So minus c squared should be g rho sigma u rho u sigma. So what is this? Our metric is diagonal, so we have no mixed term. We only have a tt term and an ij term. So this is gtt. ut is n plus delta ut. Yeah, from this formula here. If rho is t, then this is a 1. And here for rho I have written t. And this is squared, right? Because it comes twice. And then I have the spatial term. There's no mixed term, no it term. U rho, u i. Ah, okay. Here, then this term is 0. If rho is I, then this is 0. So I have only this perturbation here, delta ui, delta uj, and this is already of second order. That's what we neglect usually. Yeah, we are doing first order. Negligible. Yeah, because it's second order. It's a product of linear perturbations. So what is GTT? GTT is minus c squared a squared 1 plus 2 phi. And then I multiply this out. And I get n squared plus 2n delta ut plus something which is quadratic or higher order. So this is minus c squared a squared. If I multiply this out, I get an n squared plus 2n delta ut plus 2 phi n squared plus the higher order terms. Okay, so in zeros order, this is first order, this is first order, so I have to compare this with this here. I get minus c squared is minus c squared a squared n squared. That's the zeros order terms on both sides. So this means, can I solve this? I think n must be 1 over a, right? N must be 1 over a. Plus or minus, but we want to have it future pointing. Yeah, so it should be with a plus sign in the direction of delta rho t. And the first order, then these two terms have to cancel each other. So we must have 2n delta ut plus 2n squared phi must be 0. 2n, 2n. So this means delta ut, I know it's upstairs, sorry, is minus n, that's minus 1 over a, times phi. That's it, right? So our time-like vector field is u rho is n times Kronecker, and n is 1 over a, delta rho t, minus 1 over a phi, minus phi. That's our vector field. Phi, this is, nonsense. Slowly. This is the first term. And then I have plus delta ut, delta rho t. This is minus 1 over a phi, delta rho t. And then I have the term when the rho is a Latin index. So this is plus delta ui, delta rho I, right? We don't get any condition on delta ui. Yeah, delta ui gives the term of higher order. We don't get a condition on this coefficient here. So that's our vector field. And now we have to solve the geodesic equation. Oops.
Delta ui can be arbitrary.
I'm sorry?
I mean, delta ui can be arbitrary in this because we don't have a...
Yes, yes. If we just require this normalization condition, no, this one here. If you just require the normalization condition, nothing else, then the delta ui can be an arbitrary quantity which is smaller first order. If we require that it satisfies an equation of motion, yeah, so that it is a dust, so that it is geodesic, or that it satisfies the Euler equation, then we do get a condition on the delta ui. But at the moment we don't require anything like that. So, and then we have the light-like geodesics. I think I do this on the other board. Oops. The light-like geodesics. Now that's the ingredients we know for we need for the redshift formula, right? We need our observer field, and we need the equation for the light-like geodesics, which connects the two observer fields. And so our light-like geodesic is now something like T of S, which is an unperturbed light-like geodesic plus a perturbation, something like that. Yeah. So that's the light-like geodesic in the background, Robertson-Walker spacetime, and that's the perturbation. And similarly for the spatial component, xi of S. S is an affine parameter along the geodesic. Yeah, it's the same meaning as in this picture. Yeah, it's a parameter along the light-like geodesic. Xi bar of S plus delta xi of S. Well, and I hope everybody knows how we determine light-like geodesics. What would you do? Would you calculate the gammas and then write the geodesic equation? I usually recommend not to do this. Of course, I can do it. There's one way in which one can do it. But usually it's more convenient to use the Lagrange formalism. Yeah? So write down the Lagrangian. So the Lagrangian for the geodesics is, of course, L is 1/2 G mu nu x mu dot x mu dot. Dot means derivative with respect to this parameter S. So if you write this out, then it is 1/2 a squared. And the metric is written there. So the metric is minus c squared, or let me begin with this term, 1 plus 2 phi c squared t dot squared. This thing here, taking derivative with respect to s squared, plus 1 minus 2 phi delta ij xi dot xj dot. So we have light-like geodesics. What does this mean? It means that this must be 0, right? This means that we have a light-like curve. It does not yet tell us that it is a geodesic, just a light-like curve. It's something with 0. It's g mu nu x mu dot x nu dot. So this is, if I multiply this here out, then I have a squared. Let me see. In zeros order, I get minus c squared. Oh, let me first write. It in this form as it is written here. Minus 1 plus 2 phi c squared t dot squared plus 1 minus 2 phi delta ij xi dot xij. Because, well, this is certainly not 0, so the curly bracket must be 0, and I can solve this for the delta ij xi dot xj dot xi dot xj dot. This is just, this comes to the other side, and it becomes a plus. I have to divide by this, 1 minus 2 phi c squared t dot squared. And this is, well, if I Taylor expand this here, then I get in the numerator 1 plus 2 phi, right? If I expand 1 over 1 minus 2 phi, this is 1 plus 2 phi plus the higher order terms. So I get altogether 1 plus 4 phi t dot squared. So in zeros order, I have delta ij xi dot xj dot. That's the zeroth order on the left-hand side. And on the right-hand side, I have bar dot squared. That's a condition that I have a light-like curve on the background space-time. Yeah? And in first order, I have first order, this is a mixed term, right? So I get 2 times delta ij xi dot, and this is delta xj dot. The next term is then already quadratic, right? So 2 terms with a delta xi dot. So this is quadratic. I drop it. And here I have 4 phi t bar dot squared plus the linear term from this here. This is t bar squared 2 times delta t dot, right? If I multiply this out, then I get this here. 2, 2, 2. Hmm? You're right. Here's a c squared. This is where? Everywhere here, right? Yeah, okay. Okay, this was the condition that we have a light-like curve. And now we have the condition, that we have a geodesic. And the geodesic equation is, of course, dl dx rho dot is dl by dx rho, the Euler-Lagrange equation, right? So here is a Lagrangian. So this gives what? This gives g rho sigma x sigma dot, right? It's a derivative of this expression with respect to x rho dot. Term comes twice, this kills the 1/2. And here I have d by dx rho, there's a 1/2. G mu nu x mu dot x mu dot. Okay. Now I can calculate this here. So this is, okay, let me do it slowly. D by dx rho. What is this here? This is a squared times the curly bracket minus c squared. No, there was 1 plus 2 phi. C squared t dot squared plus 1 minus 2 phi delta ij xi dot xj dot. Okay. So this is 1/2. Let's differentiate the a. Actually, the a depends only on t. So it's 2a dA by dt delta rho t. Yeah. If rho is t, then I get this here. This is the derivative of a squared. And if rho is a Latin index, then I get nothing. So I get a 0 because a doesn't depend on the xi's. The scale factor depends only on t. So I've differentiated this here, and then I have the curly bracket, but the curly bracket is 0. The curly bracket is 0 because I have a light-like curve. Yeah? So this here is 0. So where else do I get something when I calculate this derivative? Only if it hits the phi, right? It's a partial derivative, so the x rho dot are considered to be constant. So it's only a differentiation with respect to the coordinates. And the only other thing, except the a, which depends on the coordinates, is a phi. So I have plus 1/2 d by dx rho when it hits the phi. So when it hits 2 phi. And this comes with minus a squared c squared t dot squared minus delta ij xi dot xj dot. Okay? Oops. So of course a factor of 2 cancels. So I have d phi by dx rho. And then I get here what? This we have just calculated. This is this here. So it is t dot squared and then something which is of first order, but this is already of first order. So I have, oh no, here, I should point to this here. Yeah, this is already of first order. So I only need the 0th order term, and the 0th order term is t dot squared. Did I again forget the c squared? Let me see. Here I also forgot a c squared, right? So it's this here. And the a squared is in front of everything, right? So here's again an a squared. Okay, now it's correct, I hope. So this is a minus sign, then I get again a 2, a squared, c squared, t dot squared. And because this is already of first order, it suffices to consider the zeroth order here. So that's the geodesic equation. This expression is equal to this here. So in zeroth order, I have GTT, T dot is 0, because this is first order already. So this thing here is a constant. This is zeroth order, yeah, zeroth order. So this is a constant, and this is minus c squared, a squared, t bar dot. This is a constant. Okay? Constant along each light like geodesic. And if this is a spatial index, gij bar, xj dot, zeroth order, it's also 0, because on the right hand side I have a first order term. So in this case, it means that a squared delta ij x bar dot j is a constant. Well, this is just the spatial direction in which my light ray is traveling, right? And on the background, on the flat background, spatially flat background, of course, it moves on a straight line. Yeah? So this is this constant. And this tells us how the time coordinate is related to the scale factor. So this is, from this you could derive the redshift formula in the background spacetime from this expression. Okay, but we want to have it in the perturbed spacetime. So in the perturbed spacetime now, we have, I want to calculate this expression there. Let me see. How do I do this? Yeah, the redshift formula. What I need to know, what do I need for the redshift formula? I need this expression here. I need this expression. So let's calculate it. So let's calculate g rho sigma x rho dot u sigma. And let's see how this changes. This gives the redshift formula. So this is, to calculate this derivative, I use a product rule. I differentiate this and leave the u sigma constant. Then I have this here, and the u sigma is left constant. And then the term where I leave this constant and differentiate the u sigma. X rho dot u sigma dot. And this is what we get from the geodesic equation. So from the geodesic equation, we have that this is equal to this term here, minus d phi by dx rho 2a squared c squared t bar squared. This is this derivative here. And what was u sigma? U sigma was, where is it? Here it is. Oops, here is u sigma. We have to read sigma instead of rho. So it's 1 over a delta sigma t. And then the first order terms, but this is already our first order, so we are done. Yeah? That's the only zeroth order term we get. The other terms are of higher order. And then this here, plus g rho sigma x rho dot u sigma dot. Well, this has a zeroth order term, so I have to calculate, to write down now every term. delta sigma t, no, minus 1 over a phi delta sigma t plus delta ui delta sigma I. Ah, these are two different deltas, right? That's a chronic, that's a perturbation.
I think in the first one there is also a mistake. Either should be two sigmas in the first term or two rows.
That's a good remark, yeah. What have I done here? This is a row, this is a row, this was correct. There's a row, sigma. Yes, this is a sigma. Look, this is a sigma. Sigma is a speaking index here. Thank you. Here it's okay. Rho, sigma, yes. That's it. Okay, and yeah. Now we are more or less done. Oops. Wait. Let's see if I can. Here. So let me continue with this expression. So what we are calculating is this here, x rho dot u sigma, and the derivative of this is this here. 1a cancels. Anything else? Where this Kronecker makes this into a time derivative, minus d phi by dt, 2ac squared, 2ac squared t dot squared, plus 1 over a delta sigma t. This means gtt t dot. 1 minus phi, right? 1 minus phi. So these two terms here, these two terms. And then the last term, they have a delta sigma I. So I get Latin indices here. xj dot delta ui. Okay? Oops. Yeah, that's more or less. I can write explicitly the metric coefficients. Then we are done. Minus d phi by dt, 2ac squared dot plus 1 over a t. Well, let me write this as this t dot, and gtt is 1 plus 2 phi with a minus sign, c squared, and this 1 minus phi. Okay, that's a middle term. And this here is just a squared delta ji. I forgot the a squared here, right? gtt also has an a squared. So this is 1a upstairs. A squared delta yj, 1 minus 2 phi xj dot delta ui. Okay, so this is first order, and this is zeroth order. Okay. So this is everything first order. What do I get here? If I write here the zeroth order, minus a c squared t bar dot, I get here 1 plus 2 phi minus phi plus phi. And if I write the first order here, minus a c squared delta t dot, then I get just the 1 here. And the last term, this is already first order, so this term can be omitted. A squared delta ji, and this is zeroth order delta ui, and I think that's it. Okay, this is the formula I wanted to derive. So we can now, because on the left-hand side I have a derivative, right? This is our final formula, which gives us a redshift in a perturbed Robertson-Walker spacetime. And we will also need next time these conservation laws here, these constants of motion. I should write them again. No, the other board. Oops. Here, these two laws. These two things are constant. Yeah, that's what we have to keep in mind. Well, c is of course a constant. Yeah, so this is a constant. That's a statement. Yeah, minus c squared doesn't change anything. So a squared t bar dot is a constant along each light ray. Of course, it takes different values for different light rays, but along each light ray, it's a constant. And also this here, a squared, where the Kronecker is a constant, a squared x dot j bar is a constant. Is a constant. So that's what we will need next time. So with the help of these formulas where we can integrate this equation now, yeah, we just write integrals in front of both sides, integrate over the curve parameter s, and then we get the expression which we need for the redshift formula. And on the right-hand side, we have an integral over certain quantities, and the integration is over the light ray. And that's the reason why the formula which results from this is called the integrated Sachs-Wolf effect. Yeah? So if we integrate this, integration over light ray, and we will do this next time, over light ray, gives the so-called integrated Sachs-Wolf effect. So this calculation was done for the first time by Rainer Sachs and Arthur Wolff in 1967, I think, 67 or 68. And well, this is really one of the most fundamental papers in cosmology, because it allows to calculate how perturbations in the space-time geometry produce perturbations in the cosmic background radiation. Yeah, if we know the redshift along each light ray, the redshift of each photon, how this is affected by the space-time geometry, by the phi, and by the variation of the velocity field, then we know how the cosmic background radiation changes. So that's why this is so important. So this is what we will do next Tuesday. So I will discuss this for. We have not yet used the field equation. Yeah, we have, as far as the observer field is concerned, we have only used that it is normalized, nothing else. Yeah, a normalized perturbation of the standard observer field. So if we had a little bit more information about the observer fields, then we can further modify this equation, and then we will discuss what we get and for which case we have an effect on the photons, and for which case we have not. So that's the last thing I will do in perturbation theory, maybe 45 minutes or so on Tuesday, and then I will speak a little bit about Bianchi models, exact solutions which are not isotropic. Yeah? This is perturbation theory, so it's solutions of the linearized Einstein equation, and there are also exact solutions without isotropy, but then we have to require homogeneity, because otherwise we cannot solve the equation, and that's what one calls the Bianchi equation. Okay, any questions to what we've done today? If not, then I wish you a happy weekend.